Welcome. I'm Dr. Morton, and I'm going to record a video now on the HEX Pad quiz. This video is going to cover part of the information, but part of the information is also in a document, which will be on Blackboard. The whole purpose of this is I'm continually searching for ways to try and teach how to develop algorithms, and I think that's a really challenging thing to do, and I'm not so sure I know how to do it. But the focus of this exercise is to give you a chance to work on an algorithm, and maybe it'll help you identify where you need to do a little work in developing algorithms. So you've probably been exposed to a little bit of that during your Introduction to C course, because whenever you write a program, you have to figure out how you're going to do it. And by the time you've finished, you have memorialized your algorithm in a deterministic description in the form of a computer program, and it either works or it doesn't. And so that's really a good way to practice algorithms. But those algorithms generally don't involve hardware. So this algorithm is going to involve a little bit of thinking about how you do the hardware in conjunction with software. So I hope overall this exercise is actually fun for you. The quiz will be fairly straightforward, and all you have to do is get at least 50% of the questions right. You get full credit, 100%. And if you get less than 50, I'll probably graduate it down a little bit. If you don't do it, you'll get no credit. So obviously you need to do it. And I don't want you to spend more than an hour or an hour and a half trying to think about the algorithm. Hopefully I'll keep this video so it's fairly short. All right, so let's get started. So first off, let me show you the finished product that I did, and so you can see how what I did works. And that'll at least give you a bit of an idea, and then I'll kind of disassemble it, and then I'll show you the parts in the little worksheet that'll be posted on Blackboard. I'll also try and describe some of the thinking that I put into it to give you a little bit of an idea of some of the other things that I sort of sorted out that you don't really have to. Okay, so with that, let me transition over here. So here's kind of the setup. Now this is actually the membrane pad that I want you to interface, and I'll talk about this in a little more detail, but you'll notice it's got this ribbon cable, and it's attached with this plug. And I made a little board that sits on top of our Viva board. These Viva boards, one of my former students who's been out now for maybe 10 years or maybe more. Anyway, he lays them out in Eagle for me because he's just a whiz in Eagle. And we order them from China, and then we pick and place them in my garage, and then we have the Micro 1 students solder on the through-hole parts. And we usually use red for the prototypes, and then we use some other color for the actual boards we make. And so this one's red because it's a prototype, but it's identical to the boards that we made for the students. And I actually invite students over to my house to help me make the boards each semester, and I'll be looking for a few students to help probably the first week in January, something like that, to make the boards for next spring. So if anybody's interested in coming over and helping me do that, you're more than welcome. Just let me know. All right, so here's the membrane pad, and you'll see that it has 16 squares on it, and each square is labeled 1, 2, 3, and then A, 4, 5, 6, and B, 7, 8, 9, and C, star, 0, pound, and D. You've seen many times. You've probably seen pads that look like that, where they don't include the row of characters. But most of those pads actually do have 16 characters. They just don't have them implemented. They only implement 12 of them. Okay, so you'll notice here, this plugs into this little adapter board, and I'm going to take it apart in a minute and show you that. I also have over here a LCD display, which I think you can read, just barely maybe, and you can see it says show hex button, and then it has R equals 3, C equals 3, and D. So if you look at this, the last button I pushed was the D button, which is row 3, starting with 0, 0, 1, 2, 3, and the third column, starting with the left-hand column, 0, 1, 2, 3. So D is row 3, column 3. And if I punch a different one, like 5, that's row 1, column 1, or 2 is row 0, column 1, A is row 0, column 3, and so forth. And there's 8, it's row 2, column 1, and 0 would be row 3, column 1. The star would be row 3, column 0. And then I display that character. Oh, let's see, I guess I took it out of focus. So, yeah. I didn't mean to do that. Maybe I'll switch it out of autofocus. No, that's not. Yeah, okay. Yeah. And then let me do some more. So B, it's a little hard to see. I apologize for that. Don't really know what else to do about it. It's hard to get the lighting right. It tends to wash the screen out on the LCD display for some reason. I don't know. Oh man. Okay, it's not too bad. So you can see there's a B, and then here's a 3. Yeah, you can see that. Okay, you get the idea. So that's how it works. Now let me take it apart. So the first thing, I'm gonna turn off the power and disconnect this. So this is a CP2102. The Micro 1 students know that this allows us to send the UART signals from the PIC through a USB converter to a desktop, and they appear in a terminal window. And I did implement that. And then we also use the I2C with power and ground here, and then I had to bring out the 2 I2C pins on my adapter board because my adapter board covers up. And we have a little board on the back of this that brings these pins out using this PCF 54, I think 76 or something chip, which basically connects 8 pins that control this LCD display. It only needs 7 pins to control it, and then 1 pin to turn the backlight on and off. And we have some driver files for that, so you can do those. And then I'm going to disconnect this. So I have this plugged in to this buddy board. You can see there's a, I don't know if you can see this or not, but there's an 8-pin header in the middle of this board, that right there, that this adapter plugs into. And if you look at this, we have 8 wires, and it turns out, and I'll show you on the sheet, the first 4 wires are rows 0, 1, 2, 3, and the next 4 are columns 0, 1, 2, 3. And so every one of these buttons has 2 pieces of membrane. One's kind of bubbled up a little bit, and when you push on it, you short the top to the bottom. And the top maybe has the columns, and the bottom maybe has the rows. So we have row 0, 1, 2, and 3, and these wires run all the way to all 4 buttons. And then we have columns 0, 1, 2, 3, and the wires run to all 4 buttons. And when you short a button, the top to the bottom, you're connecting, in the case of the 4, you're connecting row 1 to column 0, and you have to your algorithm has to be able to program the microprocessor to detect that. And the way you have to do it, you have to detect both the row and the column. And generally, the way that works is you have to drive the rows with, say, a 0. You have to make sure that then you read the 4 columns, but you have those set as inputs, which means they're very high impedance, and so you can't have them floating. So that would be a problem. You have to pull them, usually up to, say, 5 volts, and then you read them. If they read a 1, which means they're still showing 5 volts, then that row is not connected to a button that's shorted to one of the row wires. that is pulled low. But if that column reads low, then the button is pushed and it is shorted. So you determine which column reads a 0, if any of them, and that tells you if there's a button pushed and which column it is in. And then you drive the columns and you read the rows. And now you switch the columns to outputs, you switch the rows to inputs, and now they're high impedance. You drive the columns that they're now outputs, you make those zeros, but the inputs, which are now the rows, you're reading those. So you have to, again, make sure those are pulled high so they don't float. Because if they float, you don't know if when you read them if they're high or low. They could be either one. And as you move things around with your hand near the pad, you might induce a voltage on that wire, and it might go from reading high to low or low to high. You don't even know. So you have to pull them high, and then we drive them low when the button shorts the columns and rows together. So now that you've read the column and you've read the row, now you know if there is a column and a row showed up, and now because you know the column, the row number and the column number, you can figure out which pin it was, and that's how that works. And so we have this little adapter board, and the reason I made this, if you don't use a little adapter board, then what you have to do is you have to have a little whiteboard, and you have to have these DuPont wires. You have to have 8 of them running all over the place, plus a bunch of pull-up resistors, plus a bunch of other stuff, plus this and also the CP2102 dongle. By the time you get all that done, you've got a bit of a mess. And if you bump or touch anything, and you're using these wires plugged into a proto board, you'll see that it'll get screwed up. So I made this little gizmo. It took me about 2 hours to make this. And what I did, I put on some pins on the bottom. You'll see that these pins stick into this header. Now I only use one row of the header, but the rows are identical. So I have two 2x10 headers here that bring out all the pins on the chip. And when we laid this board out, we laid it out on a grid that was 0.1 center. So I know that all my pins on here are spaced at 0.1 spacing. And since this board is laid out in 0.1 spacing, I could set this up so I knew it would plug in once I kind of lined everything up. And so I plug it in. Notice also here, let's see if I can bring this closer and get a nice close-up. We'll see. I don't know if I'll be able to do that or not. Maybe. So you can see here, the green wires are the columns. The white wires are connected to the rows. So remember, I'm bringing the chip actually has 20 pins, and I'm going to talk about that in a minute. And I'm only using 8 of the pins. So the green wires go to the 8 pins I'm using here. And it turns out all these are on this one side. And then the white wires, one's here, and then one's here, and one's there. They're spread out a little bit more. And you'll notice, you can barely see them, but right underneath here, there are some resistors that I put in as well. They connect to all 8 of my pins in the header that connects to the HEX Pad, and they're all connected to a bus that is then connected to power, 5 volts. And so all these resistors pull every pin up to 5 volts. Okay, when you set them to 0, though, as outputs, then those pins will read 0. And then when you short them, the inputs that input line will also read 0. But if it's not shorted, it will read 5 volts. And if you didn't have these connected, you really don't know what it would read because it would be floating. And floating inputs connected to microprocessor inputs read unpredictably. You don't know how they're going to read because they're so high impedance. You're going to induce a 1 or a 0, either one. Okay. And then these are, this is the board that, of course, the Micro 1 students use. And we make these, and again, the UTSA are touch pads, and we have a programming header here. We have an analog header here. We have our header for our CP2102 so we can connect it to a desktop or a laptop and display information coming off the micro. And we have a 2 transistor switch here and some voltage regulators here, power input here, and a switch that switches between the battery or the CP2102 header, and we can jumper here from 5 volts to 3.3 volts. And we can jumper here. We have a push button. It can be a master clear, or it can be jumpered over here to be an RB7 input. All right, so let's talk a little bit about the pins. This chip is a 20-pin chip, and so the way we set this up, we'll go through this right now. So we have a 20-pin chip. So it's a 20-pin chip, 20 pins. We have 2 pins that are VDD equals 5 volts in this case, and VSS equals ground. So now we have 18 pins left. Then we want to display which button was pushed. So we have 2 pins we're using to drive the LCD display with an I2C interface. So we have 2 pins for the ICD interface, and it happens that those are R, B, 4, and 6. Okay, and then we have maybe I'll just say this to begin with. We actually have 3 ports on this chip. We have port A, B, and C. And port A has, I guess you can't really see me. I'm blocking myself. Yeah. Maybe that's better. Yeah, that's a little better. Okay, port A has 6 pins. Port B has 4, and port C has 8. So port A has RA0 through RA5, and port B has RB4 through RB7. RB0, 1, 2, and 3 are not implemented, and RA6 and 7 are not implemented. And then port C has RC0 through RC7. All 8 bits are implemented in port C. All right, so if we have 2 pins taken up for power and ground, that leaves us 18 pins in our ports. 6, 4, and 8, that's 18. So we have 18 GPIO pins. But some of them we can't use. We have, of course, 2 pins that we're going to use for our display, so we can't use those. We have 3 pins that we use for our programmer debugger, so we're not going to use those. We have 2 pins we're going to use for our UART to USB dongle, and that is so our programmer debugger takes up RA0, 0, 1, and 3, and our UART takes up RC 4 and 5, and our LCD display takes up RB4 and 6. Okay, and then we thought we might want to use the push button, so we have 1 push button, and that's on RB7. And then I wanted to avoid using the 3 RGB LED colors if possible. So we have red, green, and blue. And it turns out if we subtract these, if we do all 3 of these, then it's 2 plus 5 plus 7, 8, 11. So that's 11 of our 18 pins. That only leaves us 7, but we need 8, so we can't use that. So we're gonna forget the blue LED. We're gonna use that pin, which happens to be RC6, and we'll go ahead and just have 2 colors of our LEDs available to us, and that would be RA5 and RC6. So when we subtract away RA5, RC6, RB7, RC4 and 5, RA0, 1, and 3, RB4 and 6, that leaves 8 pins. Let's see if you can see this. So there's 8 pins left. 8 pins left. Okay, so what are those pins? Well, let's talk about that right now. So I'm going to shift this out. And it turns out that that just arbitrarily for the rows, I used the remaining pins, which happen to be RA4, RC3, RC7, and RB5. And for the columns, I used RA2, that was the blue LED, and then RC0, RC1, and RC2. So 4 pins for the column, 4 pins for the rows. And that's what we're left with. And so that's why on my little interface board, the wires for the columns, the green ones are kind of all together because these are pretty close together, but the white ones are kind of all over the place because they're kind of spread out. And that's how that worked out. All right. And so that explains my choice of pins. So I had to do some thinking before I made this board so I could get everything hooked up correctly. And then I also had to put in these resistors and make sure my 8-pin header, all the wires coming out of my HEX pad were pulled up to 5 volts through a 10K resistor. We pulled them up through a 10K resistor. Now, if you try and put all this stuff on one of those proto boards and plug stuff into it, you will find that things wiggle around and your resistors may stop working. It may get bumped and not be fully connected. You may have a wire pop out and then you're trying to figure out where to put it back in. So whenever you can, it's really good to take some of this copper, this perf board with one layer of copper on the other side. And let me show you how that's set up. I have a piece of it here. So you can see these rows are set up. There's buses that run between the rows, and then the buses can be connected in various ways, usually power and ground, but they can be other things. And then there are all these parallel connections with 1, 2, 3, 4 holes in them. So there's four holes, and you can see from the wire. I think you can see. Let me get that a little closer, maybe. Yeah, so you can see over here that you have 1, 2, 3, 4 little holes, and they're all connected with a solder trace, and they're separated from each other. So what I did, I just took a header in the form of this kind of a thing, and I just put it in here, and then I made sure I cut my piece out so I could have a 10-pin header and a 10-pin header here, spaced far enough that they would plug into my board. And then I put the 8-pin header in between them, and then I put the resistors and all the wires connecting everything together, and I soldered them on. So using these copper pads, so that you can take this interface board, and you can bump it around, and you know, it's pretty robust. It's not going to break. You could step on it and run it, but otherwise it's pretty hardy. And as long as you get everything soldered correctly to begin with, this is not going to be your problem child. Your problem child is not going to. This isn't going to cause you trouble. And once I set it on here, I just have to line this up, and actually I have my choice of 2 positions to put it in, and I push it down, and there it is. And then when I want to connect my pad, I just line this up, and I connect it like that, and that pad is connected, and it's very robust. It's not gonna, the connections are not gonna blow around in the wind or disconnect when it gets bumped. It's gonna work very robustly. Okay. So that basically discusses the hardware. And of course you can connect it to an Arduino too. I have an Arduino here, and I can plug it into 10 pins here. I still have to do the pull-up resistors, but I can connect it into the Arduino, and then I can download the code. Don't have to write any code, and I can use this touchpad with the Arduino. I'm pretty sure they do have code to support it, although I've never used it actually, but I'm sure it's possible. But if you do it on the PIC, now you have to write your own code, and that's a little bit challenging. So I'm going to briefly, let me go to my my data sheet here, and we'll just transition over here. So here's the data sheet that's on the web, and you can see this is HEX Pad quiz F22, and so the goal is to devise the basics of an algorithm to interface this HEX Pad to a microprocessor. Here the little cable's just kind of pushed up. So there are several problems you've got to sort of address, and here are the ones I want you to think about. Make sure you understand how the pad works. You must figure out how the micro can connect to the pad and be able to electrically read which button is pressed, despite the pins being kind of in various ports, since you don't really have the luxury of having 8 pins altogether. Now you could use all 8 pins of the C register. If you did that, then you can't use C4 and 5 to drive your UART, and then maybe that's okay. It turns out I did use it, but you probably don't really need it. You could probably get by with using the entire C port. But I elected just to scatter them around, since in the software you can compensate for that. You must figure out how to connect the press button to the correct symbol that the button represents. Well, notice when you detect the button, all you get is a row and a column number, and you have to convert that column number into the symbol. So for instance, 00, you want to display a 1. 03, you want to display an asterisk or a star. And here 0, 1, so 0, 1, 2. So row 2, column 2, you want to display a 9. Here row 2, column 3, you want to display a C. So you can see, generally for that, you're going to probably need a lookup table. And I'll show you how I implemented my lookup table. Let me just bring that up here briefly. So when I wrote my code, the first thing I did, I dated it, and then notice here, I very carefully, and let's see, I'm going to pop this out. So, and I don't know if I can make it bigger or not. Maybe. But what I want you to see, though, is I want you to see, maybe I think I can make it bigger, yeah. So I want you to see, so I use pull-up 10Ks on all 8 leads, and then 4 columns, RA4, RC3, RC7, RB5, and 4 rows, RA2, RC0, RC1, and RC2. Actually, I believe I switched those around. I should correct that. Yeah, I'm sure I did the rows. The rows are, yeah, I need to switch that. And maybe I will right now. Yeah. Okay, so anyway, yeah. So you want to keep it this as straight as you can. And then I drew a little picture here. I put in all the symbols, and I showed the cable coming out, and I showed the first 4 pins were rows 0, 1, 2, 3, and the next 8 pins were columns 0, 1, 2, 3. That's how the cable's set up, and that's how I interfaced it. And then I talked about how I set up the I2C interface. I did have to bring out RB7 and the 2 pins for the I2C interface were covered up by my board, and I didn't have any other way to get to them, so I added 2 little pins to my interface board so I could plug in the data and the clock pins for the I2C interface, the I2C interface. All right, and then I had a bunch of includes, and then a bunch of my configuration words, a bunch of defined stuff, my function prototypes, and then then I did some basic setup stuff, and then I knitted my I2C. I had knitted my COM so I could use my UART and my CP2102 dongle to connect to the USB port on a desktop or a laptop. And then I set up my initial 2-line by 16 LCD display using the I2C interface with it. And then notice here I have a little lookup table, and and you can see I have all these entries in my lookup table, and so row 0, column 0 is a 1, row 0, comma 1 is a 2, 3A, and then space for 4. Now there aren't 5 columns and not 5 rows, so this is just what happens if you go past that. But I didn't actually implement that. I skipped that, but I probably should have put that space in there so it would erase and display nothing when it's not detecting a push. But in any event, and then the next row, 4, 5, 6, and B, and 7, 8, 9, and C, and star 0 pound D. And then since I had, what I do, I start my row and column at the default value of 4, and then that's what it stays if it doesn't read a push. All right. So anyway, so I use a lookup table for that, and I want you to think about that. And then I did a little printout here, and basically this is all I did. I wrote a little routine to get the index, and so that's how I did it, to get row val and column val, and I put that little routine down here, and so when I put in the column value, let's see, get HEX Pad. That's the get index. Never mind. So here's the one that actually reads the pad, get HEX Pad, and you can see what it does. I'll just giving you some hints here. So here's the function. Okay, this much. That's the function. And so what it does here is it sets all of the outputs to 0, and I never change that. And then it uses the pin direction register called the tris register for A4, C3, C7, B4. So we set, and it says columns, but those are actually the rows, and and then this says rows, but those are actually the columns because I switched it around, I guess, is what happened. Anyway, so once I set it up to read the, so actually in this case I'm reading the columns. I should switch these because I did change that. And down here, and read the columns, and now read. Well, anyway, well, I even switched the variables. I'll fix it one of these days. All right. So anyway, you can see I set them to 1, which is input, set these to 0, which is output. And so I'm driving these to ground with my output at 0. And then I'm making these inputs, and then I read them. And here's where I read them. And notice I read RC2, shift it 3 to the left, or that with RC1, shifted 2 to the left, or that with RC0, shifted 1 to the left, and or that with RA2, not shifted at all. And that gives me my 4-bit row value, which is actually the column value. And then I do the same thing here. I switch it around. Instead of outputs, I make them inputs. Instead of inputs, I make them outputs. And now I read the column value. And I do RB5 shifted 3, RC7 shifted 2, RC3 shifted 1, and RA4 shifted none. And that gives me my 4 column values in a 4-bit variable. And that's all I do. And then here I turn them into the actual row 0, 1, 2, 3 and column 1, 2, 3 because what they actually read, E, D, B, and 7 for the 3 rows. And if they don't read one of these, then I assign the result to 4. And that's all there is to it. All right, so I kind of showed you how I did it. What I'd like you to do is do some thinking. Just see if you can figure this out on your own. I'd like you to just maybe spend an hour, maybe an hour and a half, and then go online and take the quiz. And the quiz will be available basically all day Wednesday, as will this video. And so make sure you do it on Wednesday, and have a happy Thanksgiving. And that will be the end of it. Oh, before I sign off, let me do one more thing. I wanted to finish that document. I want to go through the rest of it. So you watch the video, which I just finished, and then you can see how I've drawn some pictures here. And you can. This is a better picture of what this perf board. This is actually slightly different than the one I used, but it's the same idea. Here they have 5 holes together, which I actually would have preferred because I just had 4. And then they have the buses, the double buses running in between, usually power and ground, but it varies. And this is what the board looks like. This is different color, but same exact things. And you can see the resistors here soldered in. And of course, you have to be somewhat careful that you don't short things out. But and the green wires are the rows, the white wires are the columns. I think that's right. No, white wires are the rows, green wires are the columns. I think. Now I'm totally confused. And here's how the board we use. This plugs right in here, and you can see the 2 10-pin headers. Here's the bottom side of it. These are the 10-pin headers that pick up all the pins from the chip, and then this is the 8-pin header that actually sticks up on the top of the board, so I can plug my HEX Pad into that. And here's how I set up rows and columns, and I think that's it. So that's pretty much the rest of that document. Okay, I did want to just briefly go through that. All right, we are going to stop the recording here. Happy Thanksgiving.